Hi, my name is Oliver Geißendörfer. Today we're discussing the usage of LiDAR vibration monitoring, one of our research topics at the Chair of Engineering Geodesy at Technical University of Munich, with a special focus on structural health monitoring, specifically for assets like bridges. Traditionally, we analyze periodic behaviors as well as mode shapes using fixed sensors like IMUs, here you can see them in blue, or GNSS sensors displayed in green. However, these require physical attachment and shared reference frame in space and time for data analysis. In the world of LiDAR, we face a trade-off because individual points are generally sampled with a high temporal resolution, but at different locations. 2D profiles provide better spatial understanding with a still sufficient temporal sampling rate. However, analyzing 2D profiles often imitate point-wise observations and heavily depend on its orientation. Our goal is to bridge this gap by combining LiDAR with time domain frequency analysis for enhanced spatial understanding. To move beyond simple analysis of time series, here with the subscript I, we employ spatiotemporal parameter estimation. We model the signal using a time domain approach, where we define the model by the mean, amplitude, and phase along a predefined frequency. To handle complex real-world vibrations, we utilize Fourier series expansion to decompose the signal because of its linearized properties. This allows us calculating the amplitude and phase using the estimated substituted coefficients A and B for each frequency m. Switching all spatially dependent parameters to a function allows us to simultaneously estimate frequencies and model properties across different continuous spatial locations rather than just at discrete points. We validate this approach using a controlled experiment using a Leica P50 laser scanner in profile mode at 50 Hz temporal sampling and a 3 mm point spacing at 10 meters distance. Observing a wooden plane mounted on a toy train carriage. The setup induced a repetitive movement with a limited spatial volume. To process this data, we need to separate the geometry and the movement using a principal component analysis, short PCA. By identifying the eigenvectors, we can isolate and analyze the repetitive movement, which corresponds to the second principal component, while the first principal component contains mainly spatial information. Along this separation, we can imitate equally sized sensors with no gaps between them. Our results demonstrate that we can fit a spatiotemporal model approximating periodic movement in space and time. Here we can see the mean and two amplitudes of the induced movement. By adjusting the sensor width in our processing from 10 mm down to 1 mm, we can significantly refine the convergence of our variables. When switching from individual time series, here in black, to temporal connections, here in blue, and to spatiotemporal models using polynomials in orange or B-splines in cyan. Essentially, this method exploits the sampling rate of LiDAR in both space and time. It allows us to use spatial proximity to implement spatiotemporal connections, giving us a contactless, time-synchronized way to evaluate vibrations of entire surfaces rather than just single points. When you are more interested in further information, you can find the full paper and the GitHub code via the QR codes. So, thank you. And please hit like and subscribe. Stay curious and see you at TUM.